Welcome to the deep dive. Today, we're getting into dynamic programming, DP.
Exactly, DP.
It's this really powerful way, this algorithmic approach for tackling complex problems. The idea is you break them down, simpler pieces, manageable ones.
That's the core of it.
And our mission, really, is for you to see how this, well, seemingly abstract idea is actually running behind the scenes in a lot of tech you use.
It really is everywhere once you know what to look for.
What's wild is the name dynamic programming. Richard Bellman, back in the 1940s.
Yeah, way back.
And the programming part. It's not coding, right? Not like we think of it today.
Not at all. It meant planning, like creating a schedule or a method, a systematic approach.
Okay, a plan. And the core idea is, well, it sounds simple but powerful. Solve each little subproblem just one time.
Just once. And you store that answer.
Just do it.
Then, and this is key, you reuse that stored answer anytime that same subproblem pops up again.
Ah, so no recalculating the same thing over and over.
Precisely. It cuts down massively on redundant work, makes the whole thing way more efficient.
Right. But it doesn't work for every problem, does it? You need certain conditions.
Correct. For a DP to be effective, you need two key properties. The first one is optimal substructure.
Optimal substructure. Okay, what does that mean practically?
It means that the best solution to the big problem can be built directly from the best solutions to its smaller parts.
Like pieces of a puzzle?
Kind of. Think about finding the shortest route on a map. If the best route from A to B goes through C, then the path you took from A to C has to be the shortest path between A and C.
Ah, okay. The parts have to be optimal for the whole thing to be optimal. Makes sense. Got it. What's the second property?
The second one is overlapping subproblems.
Overlapping,
Right.
meaning you keep seeing the same smaller problems again and again.
Exactly that. The classic example is computing Fibonacci numbers recursively.
Oh yeah, that gets slow fast.
It gets incredibly slow because you recalculate F3, F2, F1 loads of times. DP avoids that. It calculates F3 once, stores it, and just pulls out the answer next time.
So solve it once, store it, reuse it. That's the mantra.
That's the DP mantra.
Okay, so we know why we do it and when it works, but how do we actually, apply it? You mentioned two main ways, top down and bottom up.
Right. Two main strategies. First is top down, which people often call memoization.
Memoization. Like writing memos?
Sort of. You start with the main problem, like a normal recursive approach, but you add a cache, a memory.
Okay.
Before computing any subproblem, you check. Have I solved this already and saved the answer?
Uh-huh.
If yes, you just return that saved answer quick. If no, then you compute it, save the result, and then return it.
So it's like recursion, but with notes to self so you don't repeat work. Clever.
Exactly. Recursion plus caching.
And the other way, bottom up.
Bottom up, also called tabulation. This is different. You don't start with the big problem. You start with the smallest, simplest subproblem.
Base cases.
The base cases, precisely. You solve those first. Then you use those solutions to solve slightly bigger subproblems, and then bigger ones, systematically building your way up.
Like building with Legos from the ground up.
That's a great analogy. You fill a table, usually, starting with the easy answers and using them to find the next set of answers until you reach the final solution to the original big problem.
Okay, that's structured building.
Yeah.
Now I see why Bellman used the word programming, like planning. It's very systematic.
It is. It's a really fundamental technique in algorithm design.
Thinking smarter, really, not just throwing more computer power at it.
Absolutely. And the benefits are huge. Efficiency, first off. That Fibonacci example. DP takes it from exponential time, totally impractical, down to linear time, a massive, massive speed up.
Wow, okay.
And second, because of that optimal substructure property we talked about, DP guarantees you find the globally optimal solution for problems that fit the model. Not just a good solution, the best one. That's critical for optimization tasks.
And the applications, they're everywhere, aren't they? Not just textbook examples.
No, definitely.
You mentioned shortest paths, like in GPS, right? And the knapsack problem. That sounds like logistics, packing things efficiently.
Exactly. Resource allocation, cargo loading, fitting the most value into a limited space. Also, database query optimization, figuring out the fastest way to run a search.
And bioinformatics, DNA stuff.
Yep. Finding the longest common subsequence between DNA strands helps understand genetic links. And research is always pushing it further. Quantum computing speedups, finding optimal paths over tricky terrain. It's still evolving.
It's really quite something. So maybe a final thought for our listeners.
Well, yeah. Given how systematic DP is and how powerful it is for solving these complex optimization and decision problems, think about this. How might this fundamental idea, dynamic programming, be working silently, unseen in the technology you interact with every single day, from your phone to the web? Where else is it optimizing things for you? It's worth considering its hidden reach.